Hello, guys. Welcome to another episode of Global Papers. Super excited to have Jianyuan Wang with us today to share about his paper VGGT Visual Geometry Grounded Transformer. Welcome to the show, Jianyuan.
Thank you, Michael, and thank you, Chris, for the invitation. Should I first do a quick self-introduction or something else?
Yeah, of course. We'd love to learn more.
Yeah. Hi, all. My name is Jin Yuan, and feel free to call me Jay. Currently, I'm a PhD student at Meta AI and at the Visual Geometry Group of Oxford. Basically, my research topic is focusing on 3D reconstruction from some older stuff like classical structure from motion towards the recent deep-based ones like post-diffusion, VGGS or VGGT. Yeah, I guess that's all.
Okay, cool. And could you share a little bit about any motivation, any prior work that you were involved in that kind of motivated you to do this work on VGG?
Actually, I have a complete slides for this. So here are some animations. Let's just a bit. So I would like to start from classical structure from motion. Basically, reconstruction is a quite old problem in vision. I think in robotics it's kind of simplified because we have a lot of sensors can be used there. But we in vision, 3D reconstruction is a very core problem for decades. And from the very early stage research to the Hartley and Zimmer's book to the recent core map. After after 2016, we have some trials to solve the reconstruction problem by deep learning methods like SFLearn or like GeoNet, like our previous work, Deep SFLearn did, RealPulse, or more recent Duster. But all of these previous paradigms, they were using a pairwise design. I think SLAM is probably more related to robotics field, while SLAM also focus on pairwise design. But here is a problem that if we train a deep model in a pairwise manner, it means the model can only see two frames during training. During testing, people need to do some test time fusion, test time optimization to fuse the pairwise prediction into the whole reconstruction or the whole thing. That's a problem, right? We can see a mismatch here. We can see that the model cannot really leverage the information from the whole thing. And that's the main motivation that we move from the main motivation for my whole series of work, from post-diffusion here to VGGS fan, and then to the recent VGG transformer. Basically, here's the whole idea. And then what's the difference between VGG transformer and our previous work? Basically, in VGG transformer, we hope to make it deep-only framework without any geometric priors, without any like multi-view geometry supervision signal or multi-view geometry, some inductive bias inside the framework. And I guess that's why it attracts kind of attention in the community, because the community also thinks, okay, it's time going for a fully deep or say deep only framework now. Yeah, here is the basic motivation.
Sorry, could you just explain a little bit on this concept of pairwise?
Oh, yeah. Yeah, please go on.
So, am I right to say that when you say pairwise, basically all this prior work, effectively you are relating one image to another image? Whereas in
Yes.
your case, you are taking a whole sequence of images.
Yes, we can see
Yeah.
so. Right. Are you familiar with Duster?
Yes, vaguely familiar. Yeah, yeah.
Yeah.
I can't say I'm super deep into it. Yeah, but I know it's a very very selective work.
Yeah, no worries. Let me share if I can have a screen of Duster. Basically, taking Duster as an example, during training and during the first day of testing, it will only input two frames, I1 and I2, and then predicting the point map of these two frames. Then, during the whole testing phase, such methods will perform such prediction on n times n minus 1 pairs over all pairs, while n is the number of the total frames. In this way, we will have n times n minus 1 predictions, and then they use some visual geometric consistency to fuse all these results into the final reconstruction. That's why I would say it's pairwise, because it is based it uses two frames as the basic components.
So 2 frames and finding the poses. So in order to reconstruct this frame. And the reason that all these prior works do 2 frames is that mostly just because of basically the loss of the training is easier to set up, or is there a particular reason for that? Just makes more sense that way.
I think that's the habit, that's the tradition inherent from the very old stuff, classical reconstruction methods.
Yeah. Okay, great. And then so you're saying so some of your prior work has already been moving into multi-view registration, right? So not just pairwise anymore. But now you want to get rid of so the difference here is that you're not even going to do the registration step. You're just going to purely end-to-end reconstruction in the point cloud. Okay.
Yeah, that's the case.
Cool. Yeah, then I guess could you give us an overview of how you set up this whole VGGT?
Or you mean the framework?
Yes, yes.
Yeah, sure. All right, just switch up and down to find the correct slide here.
Yeah. Yeah, no worries. I'll cut all these out later on.
I think this is frame.
Mhm.
I'm sharing it. Does it look correctly in your face?
It's good, it's good. Yeah, it's
Okay.
perfect.
So basically, in VGG Transformer, I would like to first highlight that we hope to design a framework that can accept arbitrary number of input frames. So here in this figure, we use 3 frames as an example, but actually it can be 10 or 200 or something. And in more details, during training, the model will see around 2 to 24 frames. And during testing, we validated it can work with 1 frame, 2 frame, 200 frame, or even more. Okay, here's a basic idea here. And in more details, given several input frames. Okay, let me go to this slide. Given several input frames, we first use Dino to patchify the input frames into several image tokens. Basically, patchify here means the p times p pixels, they will be viewed as one patch, and one patch is a small grid, small grid component here. And then we will add a randomly initialized camera token into such image tokens. This camera token was designed to aggregate the information for the camera parameter estimation. And such a camera token is randomly initialized as a learnable component of the network. So it means it is not specified for the sequences, for the input sims. No, it was just something like the class token in Dino. And then we feed the concatenation of the camera token and the image tokens into a module called alternate attention. Basically, it's nothing special, but just first global attention and then frame-wise attention, and we alternate between global frame-wise, global frame-wise, global frame-wise for multiple times. With this, we output the aggregated image tokens and the aggregated camera tokens.
So by global frame-wise, what you mean is that in a global attention layer, all the different tokens from all the different all the different images that you have observed can then attend to one another. Whereas frame-wise, they're restricted to only attending to other tokens from the same frame, or is it something else?
Exactly, that's the
Okay.
case. Yeah, and finally, for the output, we use a small transformer called camera head to convert the camera tokens to camera informations like intrinsic and extrinsic. And then we use DPD head to convert the image tokens into like depth maps, point maps, or 2D tracks. And I think something I made to. Okay, basically this framework we specially designed it to be very simple and you just use very standard components because we hope it can be something that can be modified by the community for their customized usage. That's why we hope our own framework can be very simple. And the only special, I would say, kind of special design is alternative attention here, as Chris just asked. So I will hope to briefly introduce why we need to make such a design. First, it is very simple that I think every person can think of it. Just first global and then local, global and local. It is very common in a lot of research. And why do we need global attention? Because we need some multi-view consistency, right? We have several frames as input. We want to reconstruct the scene. It means the reconstructed result should be consistent across different frames. That's why we need more global attention to ensure multi-view consistency. The more important one is why we need frame-wise attention. First, it enhances performance, but it's fine. I designed it for a more important reason is that we hope use frame-wise attention to remove the need for frame index embedding, which can hence ensure the permutation equivalence. Let me take this into more details. So, for example, let's remove the frame-wise attention. The framework here will be just a global attention, like very standard transformer architecture. We show LLM or the LLM in natural language processing. They just use a big transformer layer to let all the tokens attend to each other. But here is a problem that in our case, okay, let's back to the basics that.
So wait, why?
Sorry,
So
I
why
hope
couldn't I use a positional embedding? I guess
Yeah.
is that the question? Like, why can't I use a positional embedding on top of the global attention?
Yeah, that's a question, and the answer is when you enter a house, when we look at a building, if we look it from the left to the right or from the right to the left, what we see should be the same building, right? It means the order of the input frames should not affect the final reconstruction result. Does that make sense?
Yeah. So okay, just as an aside, do you use a positional embedding? I assume you still do in the frame attention, right? So that it knows.
Yes.
Yeah. Right. But because within a frame, of course, it does matter, like whether it's in the upper left corner of the image or not, right? But here but you're saying like across all of them, of course, it doesn't. It shouldn't matter at all, right? Yeah.
Yeah. We hope to remove the frame index as embedding. For example, the top 4 tokens, it should be, if we use frame index embedding, it will be encoded as frame 0. And the bottom token, 4 tokens, if we use it, it should be encoded as frame second. But if we encode such information, then the order of input images will change the final reconstruction results. That's something we don't hope to do.
Got it. Yeah, makes sense. It makes sense the way you explain it. Like, look left to right,
Well,
right to left.
okay.
It's still the
Actually,
same building.
I am curious. So like going left to right, right to left, that it makes sense that those should be invariant. But like knowing that this image follows this image in a really ambiguous environment actually does seem like it could be valuable. Is there just the case that for most images this is actually not really the case? There's enough overlap between sequential frames that they can just kind of figure it out, or is it just a? Could you explain that maybe?
That's very valuable. Why the task is more like the task specified for SLAM. So structural motion aims to reconstruct the results from unordered images without the knowledge. It assumes we will collect the images from the internet. For example, this is something called photo tourism reconstruction, that a lot of tourists over the world take photos of like Roma, and then people collect such data from the internet and reconstruct all of them. We don't have such priors. But if you know your input images all come from the same video, and they follow some temporal continuity or something, it is very useful to use such information for reconstruction.
Gotcha. Okay, so like it's not even that like you don't need the frame index, but you don't even have it under your assumption. So this is an important detail for someone like me who's more used to thinking of things from robots where it is all like a single video sequence. So in this case, you're simplifying it because it doesn't even actually all need to come from like the same sources. Gotcha. Okay. Thank you.
Yeah, but let me add one more sentence here is that we have also found it and the community, some group, after our release, some research groups have tested it that after some simple fine tuning, the model can also accept the input with time continuity, and it can work even better because in our formula, we remove the time assumption and it actually lacks some information. But if you have it, the final prediction can be even more accurate.
Do you still, in that case, do you still use the global versus frame attention? Is that still useful?
We still use it because we want to just fine tune the model.
But it seems to me that this like VGGT, it can do multiple like computer vision tasks. Like it can do the camera pose, give you depth map, give you point maps, give you like tracking, point tracking, right, across frames. How do you balance how the model is like learning multiple things at the same time?
This is something quite interesting that in the beginning I thought I needed to carefully turn the loss weight for every loss to
Yeah.
balance it. But actually in our own testing we found it's not necessary.
Mm.
The only thing we needed to do is ensure that the range, the magnitude of different loss almost stay in the same range. So for the camera depth and the point map head, we just use the same loss weight equals 1. And for the tracks head, we use the loss weight of 0.05, which because the absolute value of the tracking loss is quite large, we just put it to the same magnitude of other losses and it works. It works quite well. I think this is probably due to the fact that those tasks, they are all quite geometric tasks and they are related to each other a lot. And in this case, learning one task will even benefit another. So we don't really need to be cautious about the loss weight of each brand. I mean, this is just my observation. We actually tried several loss combinations, tried several different loss weights, and I found it does not matter that much.
Jian, can you also comment a little bit about the various type of data sets that you use to train the model? Because I know there are a bunch of different ones.
This one? Yeah, so our training data actually have around 3 type of sources. The first one is those annotated by previous structural motion methods. For example, we have COMAP. COMAP is a classical structural motion framework, which was before the deep decade. So it's kind of like, the good stuff that has mathematical support, but do not generalize that well, do not that powerful. It can work on some well-conditioned scenarios. But in these scenarios, we can use it to annotate some data and then do some filtering to get some kind of pseudo ground truth. Here is one type of source, like Core3D, like mega depths. And then another important source is synthetic data. For example, Blender MVS, Hyperscene, Habitat, Replica, Virtual Kitty, Point Odyssey, and we think you can see around half or around 60% of our training data is from synthetic data. And the third source is some real world capture by LiDAR. I think we used, where is it? Yeah, Mapletary. Here's something like an autonomous driving data set, like Kitty or Waymo nuisance, and its ground truth was annotated with LiDAR points, very sparse but accurate results. While we don't have so much data for use in this case, so its percentage is not that huge. Yeah, but basically, as we said, we have 3 types of data sources here.
I suppose you did you do any, like for example, if you use less of the synthetic data, how do you think? Do you have some sense like how do you think the model would have behaved?
This is a quite interesting. I mean, actually, we have some observations here. So synthetic data, they are really good, and if we increase the proportion of synthetic data in our training set, in our whole training data, it will increase the final prediction quality, like the smoothness of the depth map or the completeness of the depth maps. It is really good. But the problem here is currently, although we have used a lot of synthetic data sets, they are not diverse enough. As you know, most of such synthetic data sets, they are built in some synthetic engines with limited materials there. So the problem we find here is if we train our model only on synthetic data, it can work well. It can have even better performance in some specific scenarios. But in general, its robustness and generalization ability will be affected. And another point is about the core map, also the pseudo ground truth data like Core3D or DR3D or megadepths. These stuffs, actually their ground truth quality is not that high. And when we increase the proportion of such data, the performance will drop, has a clear drop. But we found if if we if we include kind of them just into the training data, such data will increase our generalization ability. So the point here is that we think currently there's still a trade-off between using pseudo-label ground truth and the synthetic data. Yeah, that's what we have observed here.
Yeah, this is so interesting to me. Like, beyond just curating the architecture, just knowing what data sources to put into the whole pipeline, it is maybe more than half the performance.
How do you determine which data sets are the best? Is this just, do you have like, so do you have some like data set that you need to use to test this? Like, how do you determine whether or not it's actually a valuable mixture, the best mixture?
I see. Actually, I just use almost the same proportion for each data set. So we did not manually adjust its ratio, but basically keep their sampling ratio in the same level. And yeah, I think another question is how did we evaluate it? I did not do some real academic like evaluation studies for this. I did not. But in the early stage of the experiments, I run several experiments and check their results visually by me, check it by my eyes. And I found such a
Yeah, that
phenomenon.
makes sense.
Yes.
Yeah. I mean, I've got to imagine running like full ablation experiments on the order of all these data sets would be incredibly time consuming and expensive. So that makes sense.
Yeah,
Yeah.
Yes,
yeah, the
so
cost of the
expensive.
compute.
Yeah.
Yeah. Actually, on that note, could you comment a little bit on the compute that you use in the end, for training this?
And you mean train a model or the whole training resources for the exploration?
Well, I think just
Just to train
just
the
on the
final
final
model.
model. Yeah, yeah,
Yeah.
yeah.
We use 64 80 gigabits A100 GPUs for around 10 days.
Got it. I see. And then the final model, or maybe it's a good time for you to talk about the results when you actually run it. I guess yeah, like I mentioned earlier before the show started, like the main reason why I really wanted to reach out to you is I find that basically nearly real time result could be very useful for robotics. So yeah, maybe you can talk us through a bit of the results.
Yeah. Okay, let's skip. Okay, probably let's also see these qualitative results. So basically here, we want to highlight that our model can accept different numbers of input frames and process them in like 1 sec. For example, here we process 64 frames in 1 second. So it's basically around 20 FPS or 30 FPS or something. And we can accept a different number of inputs, reconstruct it in seconds, have some decent results. And even if, for example, here, the input has repeated structures, textualist background, which was generally very hard for the previous methods, but here our method can handle it quite well. And this case is a case of only 2 frames as input, where there's no overlap between these 2 frames. And we can see the model can still handle it. It's some qualitative results, while let's also look some quantitative results. First,
Sorry, just those results that you mentioned, what kind of compute are you using at inference?
I mean,
Yeah.
what
For
kind of
example, this
GPU?
0.
Yeah, we were using 100. Okay, I think what you were hoping to ask here is actually the runtime test and the memory usage here,
Yeah,
right?
that's great.
Yeah, so for example, for a case of 10 frames, the point is around here. Our inference will need around 4 gigabits, and I think it's around 0.2 seconds for the inference. Is that a 0.2? I think so, yes. And this is much faster than the previous methods because we remove the pairwise design, so that the prediction is in one feed-forward run without the need for the quadratic fusion of all the results. And yeah, here basically thanks to the great work by Flash Tension, the memory usage almost goes nearly with the number of input frames, while the time usage is still not that satisfactory. It's around 01.5 or 01.6, something like this. You can see the curve. I guess this is what you were curious about.
Yeah. So
Yeah.
go ahead.
Yeah, sorry, Chris. Yeah. What do you think, like, for robotics, like something like this? Do you think it's well?
I
But
mean, I
he's
think this
using
kind of stuff is
H100.
really exciting to be able to do this kind of reconstruction. I think that there's like kind of like we were mentioning earlier for robotics is all these extra signals, like the actual images being next to each other and so on. Yeah, but it's like it's very cool to see how much we can improve these models. Like this is definitely much better than we've seen before.
Actually, I have a question here from my side because, okay, I'm not a guy in the robotics community. Okay, I hope to try some stuffs in robotics, but my question here is, in my imagination, I thought in robotics field will have some like depth sensors, like LiDAR or IMU sensors. Can we assume they are available in all robotics tasks or not? What I actually want to ask here is, what's the role of such a feasible reconstruction model in robotics?
Yeah, so one of the things that we are very interested in general these days in robotics is like being able to construct useful 3D maps that you can use to make decisions about, right? Or useful. Generally, the question of what robotics world models look like is not one that's been answered, right? So one route to it is to like reconstruct really rich 3D maps that we can interact with, or 3D graphs, or they do like there's many other approaches, of course, like just how do you put everything into memory so that it's useful. Like I think that you run into a lot of the same problems as you run into in this work, where we have things like redundant information from different frames, or like lack of context in different cases. Like a lot of the same problems need to be solved. Right. So I think, but so things like LiDAR and all do exist, but you still need to do like SLAM or localization. That's not always that easy, especially in really challenging environments. Like depends on a lot of other factors.
Yeah, I mean, the other things I would say is, you can't assume every robotic systems will have all the sensors. I mean, all those additional sensors. In fact, Tesla famously go without, right? And so, and also like in my view, then it doesn't always means that you add a new type of sensors. Like there are always like false positive, false negative among these things. So if 2 sensors, like your camera versus your sensor, tell you give you a different conclusion, then what do? Right? So there will be cases where there are these cases. So I mean, there's a lure of just using one. Since in theory, like we just operate, like mostly navigate the world with our own eyes, right? So there's a theory around maybe vision alone can do it. Yeah. So I think what your work is trying to do is basically all vision, right? So, if vision alone can give us all these like, goodies that maybe, certain robotics have to use other sensors to do. If we get it purely from vision, that is great. Then we don't have to deal with sensor fusion. Right.
I see.
Especially if you get it in real time, right? Which is why I was pointing just now, like why I wanted to reach out to you is, but you are doing it with the H100. So it's not
One day.
compute that you can
One day
you can
it'll
have
be,
that edge.
yeah.
Yeah, but today's H100 is like maybe 5 years later, like gaming GPU. So it is, it will be all these things should yeah. That's a hope, I guess.
Yeah, it makes sense. Well, wait a second. I mean, I tested and reported in H100, but if you use A100 or like 4090 GPU, it can achieve quite similar results, so it's fine.
Really? Okay.
The speed should be slightly slower, like will take around 1.8 time more time, I think so, but overall it's almost the same performance. We used 100 for testing because we only have H100, A100.
Sounds like such a
Nice
luxury.
place to be.
Yeah, exactly. Oh, sorry. I don't have 4090. I only have H100. That's good, man. Okay.
Yeah, indeed. We don't have such GPUs in the cluster.
Okay. Yeah.
Yeah, but I do notice a lot of people in our GitHub issues, they are trying to run it with like 4090 or other GPUs, and they also work well.
Got it. Cool. Yeah, sorry to interrupt you and go on this big segue too, but could you, if you can go back to like the result, like you were showing us some qualitative result. You started with the 3D reconstruction, and then the quantitative tables, right? Yep.
Yeah, I think we have a lot of quantitative tables, which may seem a bit boring for you guys. So just briefly share here. Camera poses. Here we are slightly with a only feed-forward run. We are slightly more accurate than the previous optimization-based ones, and it's around 50 times faster. And we are here. If we add the bound adjustment again, it will increase time like 1 second, and then it further improves the performance a lot.
Can I ask, like, for camera pose, like, what is the typical definition of accuracy?
Okay. Basically, what we need to do here is called AUC, which is basically just area on the curve. So for evaluation, we will have the predict camera pose regarding rotation and translation, right? We will compute the rotation and translation angular difference between one frame to all the others, and then threshold such a relative angular difference by a certain number, like 50 degrees, like 30 degrees, like 10 degrees. And then we will have a curve about the accuracy regarding the different threshold. Using this, we just compute the combined area under the curve and compute something like AUC at 30. And it is higher the better.
Yeah, I mean, yours is very impressive then. I mean, I'm just looking at the numbers.
Yeah, thank you.
Over 90. Chris, what do you think? I mean, like, can we just take camera pose is as almost like the robot like pose? If you know where the camera is on the robot, is it as simple as that, you think?
Yeah, I think kind of. I mean, if you can get a really accurate camera pose, you can do that, right? I think that there are probably differences here with the accuracy threshold for robotics is generally like centimeters or millimeters, right? Like, which is probably slight for like these big rooms. But I feel like this is probably not going to be necessarily an obstacle with this kind of stuff, right? Because you could have the scale. Yeah, it's just like it's trained on a different scale a lot of the time. My guess is that you would need to do some additional work, but I feel like the core method should work for robotic stuff. So yeah, but just being able to localize. Yeah, sorry, go ahead. That's right.
Oh, sorry.
Yeah.
Let me briefly interrupt a bit that I hope to be transparent and honest here. Although we have achieved quite quite accurate results, I think there's still a slight difference between our predictions and the sensor captures. It is definitely there. Yeah, I believe the robot camera poses it should be still better. That's what I hope to convey here. The benefit of our method is that
Well,
I'm not sure.
Yeah, go ahead.
Please.
No, I think that's probably true. Like my experience with it, from what I know about these methods, like I can't imagine. I doubt that this particular thing would give you the accuracy that you wanted. But there is still like being able to build a map like this and use it quickly. I think there's other still a lot of really cool stuff there from the robotics point of view, I think.
Yeah.
Yeah.
Yeah, that's true.
So
Yeah, actually, I have a naive question here. So, do you think such stuffs can be used as a support or cross-check in case that some like robotic sensors may have problems? For example, I'm not sure if is this the case, but I heard from some friends that counter robots, for example, if you punch a face into a robot, its depth sensors and camera sensors, its accuracy will drop a lot. Could we use such methods, such feed-forward reconstruction methods, as a cross-check to validate if a robot is in a good camera pose? Is the camera sensor of a robot in a good sense or not? Do you think this makes sense?
the question is, so is the robot in a good position where it can like observe the world, or where it can? So I think the answer is yes. I think rather than actually use it for like the actual perception for manipulation, you could use it to like take the history of all the images the robot's pulled and then use it to build up a map of where it's been and have it like, so then I can do things like go back to, I don't know, the cabinet that I saw and things like that kind of stuff. And then that should give a good prior for like if it loses localization or if it loses, right? Like, so I think yes, using it as like a spatial memory or as a way of exploring seems like, or as a way of like tracking what it knows about the world seems like really the right way to think about it for a robotics application, in my opinion. That sense, right? Is that kind of what you're thinking?
Yeah, yeah. I was thinking something like Kalman filter and use this as kind
Yeah,
of, yeah,
yeah.
that's exactly what I'm thinking.
Yeah.
And let's probably move forward. For example, we have some results with multi-view depth estimation like previous methods. Okay, we call it multi-view stereo methods, such as MVSNet or GeoMVSNet. They need ground truth camera poses input to such methods and then predict the dense depth maps. But here I think it's for the first time that in the vision field that we found a model even without ground truth cameras as input. It can achieve the similar level of accurate depth maps to those with ground truth cameras. I guess this is more a vision task, not a robotics task, is it?
This is an very important task, I think, yeah, for like being able to get good depth. Like one of the things that I think me and Michael, or like a lot of roboticists, are actually very interested in is how good you can get a lot of this spatial information without looking at these structured light cameras. So the better we can get these kinds of performances, that means that you can use cheaper sensors, you use more cameras, you can get better performance. Depth cameras have all of these failure modes too, because they work by a lot. They work whatever medium they work by. They're usually like predicting, like structured light cameras predict an IR pattern, which can be disrupted. There's certain materials that certain cameras don't wear. Like there's all these different reasons why it's actually very nice to have results like this, where yeah, um, like robotics problems are perception problems, right? Like there's sometimes other things that we can add, but yeah.
Yeah, exactly. And then we have some results for the point cloud estimation. Basically, it means directly regressing the point cloud and the two view matching estimation because, okay, our method was trained for rigid multi-view tracking, and we were hoping to benchmark it with previous methods. But we found that previous two-view matching methods, they do not perform very well in long-term track estimation. So in this way, we choose to challenge ourselves and benchmark our method on two-view matching datasets. And it seems even in this case, our method still works better than the previous two-view sorters, like Roma, like DKM or Lofter, something like this. I think here are some 3 more interesting points I would hope to share. The first is actually, as we mentioned that we were hoping to do a kind of backbone model, or people call it foundation model for the vision task. So here we want to validate that our model can also provide quite a good pre-trained backbone for downstream tasks. So for the training of our model, we mostly care about rigid tracking, which is basically assumes the input sequence is rigid, and we capture the unordered images and their 2D correspondences like this. The same color indicates the same position, while we were also hoping to try dynamic tracking, which means the input is a video and motion inside the video is quite dynamic, it's non-rigid, and we still hope to track the 2D correspondences across different time frames. And here we have some results, we have some numbers, but basically it means if we fine-tune our feature backbone with other tracking models, we can bring previous, you can see co-tracker here, which is also our previous work, from a quite not that really good results in the recent benchmarks, and we can bring co-tracker to sort out again with a number like 88, 9 in a way in connectors.
So this is implying then that you have in fact learned kind of general purpose 3D features without structural priors that can be useful. Is that the
Exactly. Yeah, and here's another example of no-view synthesis, because no-view synthesis is a more appearance level task. I mean, actually, all of the tasks we mentioned before, they are geometric tasks. They mostly look at the 3D geometry structure while kind of ignoring the appearance. But here, we also want to show that the model can also handle the no-view synthesis task very well. And one even more, kind of out of our expectation task is single view estimation. That our model was only trained for multi-view tasks, like 2 view, like 100 view, or even more. It was never trained for single view tasks. So we were a bit surprised that the model can even handle single view estimation quite well like this. Here are some qualitative examples. Well, after we share, in the beginning, we did not, we just provided the qualitative results and did not benchmark our method on molecular depth estimation because we think our method cannot work in a competitive manner there, as it was never trained for molecular tasks. But the community helped us to test it and found that even if our method was never trained for single view task, it is almost the sort in molecular depth estimation. I think this is something quite interesting. To be honest, I don't know why this could happen, and I don't know what's the mechanism behind this, but this is probably something maybe worth mentioning here.
It's really interesting.
Yeah.
You usually don't see something like this happen where it just completely nails some other task. It does again imply that somehow this is perhaps the correct training regime for training like really general purpose 3D features, which is nice. It's good. Great sign.
Yeah, that's the message I hope to convey here. Yeah, exactly.
Yeah.
And molecular depth is great for robotics,
Yeah. Yeah.
especially if you can run it real time.
I mean, multi-view depth is also really good for robotics because you can just put multiple cameras on the robot. So then that's actually the kind of thing that is very valuable because I actually think that's more valuable than the single view depth case because you can usually get better performance. Like that's why we have two eyes, right?
Yeah, exactly. I was gonna say, yeah, with two eyes we have depth. Yeah.
Yes.
Yeah. I think the good thing about vision is because cameras are cheap, and it's
Yeah.
very high definition compared to a lot of other type of sensors. So
Right.
if you can get decent molecular depth, and then it's trivial to add one more camera, and if your compute, you get it nearly real time, then you get very good depth. Then why put a depth sensor? Yeah.
Yeah, I think that's the dream is to have the robot, like the most expensive part of the robot, be the compute on board. That'd be like if you can do that. Yeah, right.
I see.
Yeah. Very cool. Yeah, I guess any other result you want to show, or if not, then maybe you could share if there are any uh drawbacks or bottlenecks that I know you mentioned something in your future work section, but you can comment a bit on those.
I think it refers here, right? Yes, actually, I think there are a lot of limitations currently, which is something we hope to overcome in the future. I don't know if it's in the near future or 1 year or 2 years later. I don't know, but basically, okay, which is related to robotics is something probably that we do not support fish air or other camera models with a lot of distortions here. I mean, if I understand it correctly, in robotics, people really like fish air cameras, especially in an egocentric manner. But in our case, we only train our model with pinhole camera. This is because the annotation for the pinhole camera is cheapest, and we can collect a lot of data for training. But in theory, I think it also makes sense to provide some good predictions for the fish air cameras. The only thing we need here is sufficient
Data.
training data. Yes. And what else?
Will Dino work in fisheye cameras very well?
No.
Is that a limitation? Yeah. Okay. So there's an additional limitation there, and that you're building off Dino, and looks like that's substantially better than the alternatives.
Oh, that's another case that because although we use Dino as our patch find model, but its parameters is updated during our training. So I think it kind of like fine tuning.
Okay.
Yes.
So maybe this wouldn't be a limitation if you had that fisheye data set. That makes sense.
Yeah. Yeah, I think the main constraint here is that the model does not see such data or does not see enough such data before. That may be the case. And what else? What else? The model currently cannot work well with such as up-down rotation. For example, if we manually make a figure up and down, and the model will predict some very strange results.
Is that also just a data set issue, or is it a more fundamental, you think?
I think from one side is a data set issue. From another side is it's harder to capture the 3D structure for the model. That for example, if we take the photo of a building in the normal manner and then take another photo of it and put it upside, I think even for human ourselves, we may have some trouble of imagining what's the correct structure of such cases. So I don't know if the model can handle it better than human with sufficient data. I don't know, but this is a non-limitation for our methods currently. Yeah,
And
and
you mentioned non-rigid deformation. Are you talking about like piece of cloth? Is that what you're saying?
non-rigid motions means, for example, deformable motions. Like when I with my hand, I'm not sure if you can see
Mm-hmm.
see my hand. You can see this cannot be described as a simple 3x4 transformation matrix, right? This is a quite complicated motion. Doesn't make sense. So basically, if some people they are dancing or running in a video, which are quite common cases in our real world, I don't know, in our daily life, but such cases are really hard for reconstruction currently. I think it is also kind of hard for other tasks. For example, autonomous driving. Although people use depth sensors or LiDAR sensors in autonomous driving, but such non-rigid scenarios they are still hard for them, especially for decision making. Yeah. For those limitations, I think most of them can be served by the data-driven manner that providing correct supervision signal. But the case is, if we want to go further beyond, okay, data is important, and then we may need to study a bit about how to serve the rigid motions.
Makes sense.
I mean, honestly, like I think every work we have some limitations, but I think clearly, I think your work has it's at least from my point of view, I'm not a computer vision expert, but it looks very impressive. And also it's very explainable because it's what you propose is a very different paradigm, right? And it's just a better paradigm. So I'm sure more people is going to build on top of your work and improve this. And hopefully some of these people are going to be robotics people who actually use it in robotics, and then we'll know how this will actually be used. But I echo what Chris said. I think a lot of this is going to be maybe mostly used in spatial memory, maybe not directly in real time, but just having a good memory of, oh, this is where I've been. You form a decent 3D representation of the world in real time. I think that's also very, very useful.
Yes.
Mobile
If it's
manipulation, navigation, things like that.
if it's a good general purpose model, I could also imagine just distilling backbone. I could really imagine distilling multi-view monocular cameras into a single point cloud being like a very extremely valuable just like side effect of all this, right? Like because if you could do that, especially if you could distill it so it would be like a relatively small model that'd fit on a Jetson, people would love that. Because then you could get, I think with multiple cameras on whatever your robot setup is, you don't need to like do a ton of training to get it. You just need to distill it to be a small enough size, right? Yeah. That's if I'm understanding right, like what your results were saying.
Yeah. I think it's a future. Yeah. Hope someone
Future
can do
work.
it.
Yeah. Hope someone else can do it. Yeah, that sounds good. Is it?
Yeah.
All right. Well, thanks for going through this. Thanks for talking to us about your work.
Yeah, thank you so much, Jian Yuan. I think, again, congratulations on the work, really impressive. And I don't know about Chris, but I personally, I felt I learned a lot the last 1 hour. Yeah, and I think a lot of this have downstream effect on robotics and hopefully more. Yeah, and in fact, I'm pretty sure some robotics guys are already thinking of how to use this as part of the stack.
Yeah, I'm sure.
Cool. Sounds good. All right. Thanks for coming on,
you.
Jian Yuan.
Right.
Yeah, it's
Yeah.
fine. Okay, cool.
Right.
Chris, so what have you learned today?
Yeah, so I thought this is a really interesting work by on reconstruction, scenery. It's reconstruction from a bunch of images, and I think I learned a lot. I feel like, in particular, I think what's really cool here is that they're talking about how you can use this to do. It's kind of a general purpose model that's the general purpose backbone, like almost a foundation model for like 3D scene understanding, because like there's this monocular depth estimation results and there's your tracking results, and like in addition to like really like state of the art reconstruction, all by getting rid of priors, like structural priors that I think were often built into these models before. And there's a bunch of little differences from like the actual robotics use case, but it's still like it's a really cool direction for us for like what we can do with it in the future. A lot of things that we talked about that I think will be cool directions that people I'm sure will build on. So we'll see more of this. And it all really does fit into this general story of how we're being able to build more and more of these components from neural network training that are like basically getting rid of a lot of the old priors we used to really need for robotics, like the obvious ones that you talked about with pairwise, and there's just tons of stuff that we don't need to do anymore. That is always exciting to see, because I think a lot of those things are potential points of failure. And what did you think?
Yeah, well, firstly, I think we should every now and then have one or two of these computer vision, like,
Computer vision
specific,
people who
yeah, to come here and educate us a bit.
Yeah.
And just my observation, like, like I went to CVPR the last 2 years, and I always find it interesting that there are always some really robotics folks showing up. And then of course you have some folks who transfer, like, kind of come over from computer vision, and then just totally embrace robotics, because a big part of robotics is vision. And human have different senses, but I don't know, I would argue our two eyes are the most important, right? And so
Right.
I think, and we have very cheap cameras, so the better we can squeeze out of, like, really cheap cameras, yeah. And like you mentioned just now, with cheap cameras, we can just put a lot of these, like, heavy lifting to better compute, in the algorithm. Then, yeah, then maybe we don't have to deal with, like, complicated hardware sensors. Yeah, because I mean, the more sensors there are, the easier things will break, right?
Right.
Especially if they
Yeah.
are very different modalities.
Yeah.
Yeah, but anyway,
Right.
cool. Yeah, we should do this every now and then. Yeah, get some CV guys come in. Yeah, educate us a little bit.
It's good. Yeah.
Mm.
Like
Cool.
computer vision is like probably the hard part of robotics a lot of the time. Not always. There's definitely times where it isn't, but it's very exciting stuff to see.
Yeah. Well, computer vision cannot solve occlusion though, so you probably need something else.
But actually, that's the nice thing about, like, these kind of time sequence things, right? Like, if I can tell if, like, part of the value of things that don't just operate on a single frame, but operate on a larger sequence of frames, is that I can, if I have a 3D model, I can tell, like, this area was occluded. I can tell, like, this is where I should explore next. Or, like, I can just forget about all that and use the backbone of a model like this to make predictions about this is where I need to go to handle this, right? I think it's true that, like, from a single frame you can't, but I actually think like using active vision you actually can. So it's like at the intersection of the two, right? Like,
as in, like, you observe the object a little bit first before you pick it up.
you have to move around,
so,
like,
okay, got it.
exactly,
I see.
right?
I see what you're saying.
So
Yeah, but
so
I
I
mean,
actually do hope to see more stuff like this that's taking in full sequences of images. I think that's really valuable for us, for everything, right? And that's how,
Got
like,
it.
I mean, there's plenty of cases where you as a person, if your head was, like, locked in place, you could not tell what was going on, but just, like, moving would solve it, right? Like,
agree, almost 95%, but I do think, for example, touch sensors will be still extremely useful.
I think so.
Yeah.
I mean,
yeah.
I still think for, like, most robotics problems, you don't actually need to do touch. I think this is a somewhat controversial opinion, I think. But,
Got
like,
it.
I think, like, 90%, like, you can get those, like, those grabbing sticks or something like that, and you can, or, like, the tool that we had an episode a couple episodes back where we had Maki with this grabber tool.
Yeah,
Like, you can do, there's so many tasks you can do without touch. There are no tasks. There are basically no useful tasks you can do without vision, right? Like, so there's definitely an order of priorities there, I think.
Yeah, for sure. That's why I caveat by saying 95%.
Yeah.
Okay. But okay, cool. Great episode. Yeah, let's do it again soon. Okay, cool.